Welcome Calculus 3 students. We're going to look at limits today. What we've been doing in 3 space has been basically algebra. Now we're going to extend our definition to limits and continuity and then derivatives and so forth after that. So we're going to try to be looking at some point, and we're going to find the limit as let's say P approaches that point, and we need to find out what that is as it approaches it from all directions and not just one direction. Now if we have a constant function, let's notice that in 2 space we have very similar results as far as limits go. Even if we are to look at our limit laws, these results are very similar to what we got in our Calculus 1 course in just 2 dimensions. We can look at each particular function if we have 2 functions, and what we say is if we're looking at the sum of those, we can take those individually. Likewise with subtraction, just a constant multiplier on our limit, exactly the same, and same with product and difference. Notice how everything is very similar. The proofs of those are in your text. In the interest of time, we'll go over examples and not the proofs at this point. In looking at example 1, I see that I have a power, I have a product, I have a constant multiplier. All of these things tell me that I can just, as long as there are no issues, I can just substitute in and find the limit of this function and the limit of this function, because they are the sum of 2 functions. So I'm just going to be using those limit laws and plug these things in. Using direct substitution and everything followed one of these laws above makes that one pretty straightforward and easy. Alright, let's discuss interior and boundary points. They do this by looking at this definition where Q is a boundary point if no matter what disk I make about Q, there's going to be points that are in R and some that are not in R, so therefore it must be a boundary point. There's some disk in P, with P as the center, where I can make a disk and all of these points will be in R, so P would be an interior point. An open and a closed set. An open set means that you don't contain the boundary points, and a closed set means that you do. If I look at this function where I have x squared minus y squared over x minus y, when I factor that, you'll notice that I get this canceling here, and this would lead to what we would have in 2 space as a whole. But it's not a whole in 3 space. What it actually becomes in 3 space is this x equal y line. In example 2, I am to find the limit. I would like to do direct substitution, but when I do, I find that I will get 2 minus 2 in the denominator, and I won't be able to do direct substitution, but I can do the same little tricks that I did in Calculus 1, and I can multiply top and bottom. Usually when you have something like this, we multiplied by the conjugate, so I'm going to multiply top and bottom by the conjugate and see if this will work. It might, and then again it might not, but I'm going to try it, and I'll do that algebra for you and then see if I can do direct substitution after that. Alright, I get an x minus 4y, and if I look over here I see that I have an x minus 4y if I pull out that y, so I'm going to do that, and I cancel that denominator, and that will suit me very well. I wrote that down for you, and this is just really nice. Chink, chink. Now I can do direct substitution and get my limit. Alright, and that one is complete. In this next problem, notice that it says non-existence of a limit, because there's nothing I can do to this thing to make direct substitution possible. In fact, if we look at the graph of it, let's see if I can get it up here. If we look at the graph of it, we can see that along this x and y axis, we can see that the function itself goes all along this x and y axis, meaning that it's not going to one particular value. So this particular limit does not exist. Does not exist. And of course that will happen, as does happen in Calculus 1 and functions in that class as well. So this little procedure that they have right here for testing the non-existence of limits would mean to look at the two different paths and show that it is going to two different values, and that would prove that the limit does not exist. We didn't have this for the last example, but that would have helped us to prove that, or allowed us to prove that. If I look at this next example, I see that it's a rational function. Everything is positive here in the denominator, so it's going to be continuous all along its domain, because I have the point filled in here at this 0, 0 spot. Okay, we have a function in A that is a composite function, and for A I see that I have the natural log of some, let's say u, and then let's look at the other function as being x squared plus y squared plus 4. And we'll call this one f, and we'll call this one g. Now this is just, h is just a composition of f and g, and this definition here tells me that I need to look at each one independently, and I can tell from there. Well, g is definitely continuous. It's a polynomial. It's continuous all along its domain, so g is continuous everywhere in R. This, however, is only continuous as long as u, and u happens to be this right here, has to be greater than 0. So as long as x squared plus y squared plus 4 is greater than 0, we're good to go. Well, seeing as no matter what I plug in here for x and y, it's going to be greater than 0, I can now say that h of x, y is continuous on, let's say continuous for all the reals in 2 space. Now let's look at B. B happens to be the function composition. Let's just say that f is e to some u, and g is this x over y. Now this is okay just as long as y isn't 0. So, and then our f function is good to go everywhere. So this is good provided for all x and y, provided y is not equal to 0. So it can be anything as long as y isn't 0. Got another limit to do. I believe I can do direct substitution on this and get there's my x, my y, my z. I can barely see them, but it's 2 squared sine pi over 2 all over z, which is 0 squared plus 4. Sine of pi over 2 is 1, so this guy right here is just going to be 4 over 4, which is 1. Okay, all done with that one. Find the points on which it's continuous. Well, it can only be continuous as long as we have non-negative numbers under here. So x squared plus y squared plus z squared minus 1 has to be greater than or equal to 0. So just shifting that over a little bit, as long as we have this condition, it'll be continuous. This means that it's continuous. This happens to be a sphere of radius 1, and it says it's continuous as long as it's outside of that sphere or on that sphere. So we'll say it's continuous at all points on or outside that sphere of radius 1 in R3. And that's it for this section. Alright, if you have any questions, just email me. Thank you.